Hello students, so in this session we are going to find out the relation between shear force and bending moment. Say any example we will take like simply supported beam with certain loading like UDL, and then we will find out what is relation between shear force and bending moment, right? So let us take a beam like this. We generally show the beam by a straight line, but actually beam is not a straight line. It has some width. It may be circular, it may be rectangular, it may be square. So beam has certain width. So for the purpose of finding the relation, I am showing the width of the beam like this. So there is a definite width of the beam. I am showing that width also, right? And it is simply supported at the ends, and there is some UDL, uniformly distributed load on the beam like this, right? So suppose the intensity of this load is W kilonewton per meter. Now to find out the relation between shear and force and bending moment, let us take a small element, a small distance in the beam, and analyze the shear force and bending moment and other forces on this small element, right? So let us take a small element like this of the beam, suppose AB, and find out what is happening in this beam, right? So I am making here separately so that it may be more clear to make the diagram. So this is our element dx. Say the length of this element is dx, right? Length of the element dx, and there is some W kilonewton load is there, UDL, and this is our A and this is B, right? So this is this section, and remaining beam is there, remaining beam. So I am showing the remaining beam also here, the remaining part of the beam like this. I am showing here remaining part of the beam with a gap, although there is no gap, but for clarity of the forces and moments, I am showing the remaining part here, this, right? Like this, right? And this is A part, right? I have cut this A part into two parts, right? And this beam is separate now. And another part is here, so let us make it also here like this, right? So this is B part basically, right? And there is UDL, and this is a roller joint here like this, right? And suppose this is C point and this is D point, so you can write C here and D here, and we have cut the point A and point B to show the forces at this in AB part, DX part. What are the forces acting on this AB part, right? So this is the intensity of this is W kilonewton per meter. Then definitely, because this distance is dx, some force will be acting at the center of this part, and that is WDX, right? And while seeing from this side, I'm looking from this side, and I'm looking at A part, this face of the part. Also, I'm looking at this face of the part, right? This part, right? What is happening here? I'm looking at this part A, this face of the A and this face of B when I am looking here. Say the shear force at this part is F, and there is small change in shear force when we reach at B. So this is F plus DF. It may be positive, DF may be positive, DF may be negative, but for the time being we have shown that there is some changes in the shear force from F to F plus DF when we move from A to B, right? I'm looking from this side, and because the body in static equilibrium, and there must be a force F because this body is in static equilibrium, a part A is in static equilibrium, so there must be some part F so that the body may remain in equilibrium, right? So F is there. Similarly, here F plus dF will be there because F plus dF is downward, so F plus dF will be upward on the other part of the B, right, to maintain the equilibrium. So F at A downward, F at A upward on two parts of this, right, when we are looking at different parts, right? So this is the case. Is it okay? Now let there is some movement here, clockwise movement, let us assume clockwise movement is there. So this is sagging movement, sagging, left clockwise is sagging, and there is some change in movement, like this. This is M plus dm. For static equilibrium, if this is clockwise at A, at the other part of A there should be anti-clockwise M, and also here there should be, if it is clockwise, it should be anti-clockwise here, M plus dm at B. So this is how we show the forces and couples. This is how we show the forces and couples. Right, at point at A and B. So now what are the forces here? F downward, F plus dF upward in section dx. In section dx we are talking about F downward, F plus dF upward, and W dx downward. So these are the forces. So if this part of the body AB is in static equilibrium, so this sum of the forces in vertical direction should be equal to 0, right? So sigma FV, sum of the forces in vertical direction should be equal to 0. So for static equilibrium, sigma FV will be equal to 0. So this implies, what is this? Implies that suppose downward forces take positive, so F is downward, W plus dx, W dx is downward, W dx is downward, and this will be equal to, these are the two downward forces, and this should be equal to F plus dF. F plus dF. This is the upward force and these are the downward forces, right? You can take any force upward or downward. We have chosen this downward, and this is F plus dF downward. Because of this is upward, and because of this is upward, right? So from here F and F will cancel out. You will get dF by dx. dF by dx will be equal to W. dF by dx is equal to W. And what is dF by dx? This is the slope of bending shear force diagram. In shear force, what is shear force diagram? It is the diagram between the x distance. We are taking this distance x. At a distance x we have taken this dx. So taking on x axis the length and on y axis the shear force, right? So that will be shear force diagram. Now this is the slope of shear force diagram. So at any point the slope of shear force diagram gives the loading of the beam at that point, right? So what it shows that the slope of shear force diagram at any point gives the loading on beam at that point, at that particular point, on that axis, right? So dF by dx is the slope. So slope of shear force diagram at any point gives the loading on the beam at that point. So this is how we find out the relation between shear force and the loading. Now we want to find out the relation between shear force and bending moment. What we can take is, what are the moments here in this small section dx? There is a clockwise couple at m, there is m plus dm moment here at b, and this will be having w by dx any moment if we take any of the cross section like this, right? So suppose take the moment about b, take moment about b, all the forces, moment of all the forces about b. And you know that if the body is in static equilibrium, then all the moments about b should be equal to 0. So if this is so, then take any moment clockwise or anti-clockwise positive for the sign convention. So m plus dm is negative here at b only. M plus dm is negative, so positive, anti-clockwise, so take it to positive. So there is a moment m plus dm, f plus df will not be having any moment because it is itself passing through b. This f will be having a moment. This is anti-clockwise, this is also anti-clockwise, this is also anti-clockwise f. So f multiplied by dx will be having a moment in anti-clockwise direction. So plus f dot dx, f dx, distance multiplied by the force, and it is anti-clockwise. This w dx is again anti-clockwise moment with distance dx by 2. So plus w dx with distance dx by 2, the force multiplied by the perpendicular distance, and that because it is acting at the center, so this distance will be dx by 2. And what is remaining? That is this m, capital M, which is acting at A, and this is clockwise, and we are taking anti-clockwise as positive, so this will be negative, so minus m, and that should be equal to 0, right? So this m and this m will cancel out. Now there is multiplication of two quantities dx and dx. You can neglect the multiplication of two small quantities, so neglect the product of two small quantities. We are neglecting the product of two small quantities like dx and dx here, so it can be neglected. What else is remaining? F dx and dm, So from here, what is the value of dm by dx? So dm by dx, so you can find out dm by dx will be equal to minus f. Dm by dx will be equal to minus f, right? So from here you will get the slope of bending moment diagram equal to the negative of the shear force. So in magnitude, the slope of bending moment diagrams gives the shear force at that point. So at any point, the slope of bending moment diagram gives the shear force at that point. So this is the relation between shear force and bending moment, which is very important, right? So slope of bending moment diagram at any point in the beam gives the shear force. I am writing only magnitude. Shear force of the beam at that point, right? So in magnitude, this will be equal to dm by dx will be equal to f, right? So this is how we find out the relation between this and this, right? And suppose now at any point if shear force is 0, if at any point shear force is 0, this is 0, this means that dm by dx is 0 at that point, slope is 0 at that point. And what is the meaning of 0 slope at that point? There will be either a maximum or minimum, right? So that's why we say that the point where shear force is 0, that point will be a point of maxima or minima, because this is the condition of either maxima or minima, right? So at a point of 0 shear force, there is either maximum or minimum bending moment, right? Because we have seen that if shear force is 0, put in this equation dm by dx will be equal to 0, and dm by dx is the slope of the bending moment diagram, and if slope is 0, it shows that either there will be a maxima or minima. So at that point there will be a maximum bending moment or minimum bending moment.